Hi, everyone. My name is Jingjing Shi. I'm a postdoc from California. Today, I'm going to talk about intrinsic alignment of galaxies, focusing mainly on the signal of star forming, or say, emission line galaxies. This talk is based on this paper posted on arXiv a few weeks ago. Galaxies lie within the cosmic web of matter field. As a result, the orientation of galaxies align with the matter field and surrounding galaxies. This is known as the galaxy intrinsic alignment. The cartoon here illustrates how red elliptical and blue disk galaxies align with the filament and each other. Studying intrinsic alignment of galaxies is important because it's a main contamination of reclancing cosmology. The galaxy intrinsic alignment induces shear alignment in the observed images, contaminating the shear signal that is caused by lensing. Ignoring intrinsic alignment signal can strongly bias constraints on cosmological parameters in cosmic shear measurement. The intrinsic alignment signal itself also contains cosmological information. Previous work showed that constraint of BAO scale can be achieved from intrinsic alignment alone in future surveys. Intrinsic alignment also shows its special power in probing anisotropic primordial non-Gaussianality. Large-scale clustering signal with isotropic primordial non-Gaussianality distinguishes from the clustering with Gaussian primordial perturbations, as shown by the first panel here. However, it shows no difference with anisotropic primordial non-Gaussianality. Well, the anisotropic primordial non-Gaussianality leaves imprints on large-scale intrinsic alignment signal. These two panels on the right show the intrinsic shear and matter cross power spectrum and intrinsic shear power spectrum. As you can see, the anisotropic primordial non-Gaussianality has an intrinsic alignment signal that is different from the isotropic primordial non-Gaussianality and the Gaussian primordial density field. The orientation of galaxies are also modulated by the galaxy formation physics. So the intrinsic alignment signal of galaxies can also be used to constrain the galaxy formation and evolution series. The intrinsic shear of galaxies, also halos, originated from large-scale tidal field. The tidal field can either elongate or compress galactic halo. The arrows here with a small g indicate the strength and direction of the gravitational field. A simple model proposed for describing such effect is a linear alignment model. The cross power spectrum between matter field and intrinsic alignment and intrinsic shear is simply proportional to the linear density field power spectrum. The linear alignment model is found to fit the large-scale intrinsic alignment measurement very well. However, it fails at smaller scales. Nonlinear alignment model is proposed to fit the intermediate scale. In nonlinear alignment model, the linear power spectrum is simply replaced by the nonlinear one. In real observation, the intrinsic alignment signal of luminous red galaxies have been detected up to a redshift of 0.7. Incoming surveys such as DAISY and Euclid will extend such measurement up to redshift of 1.5. However, no intrinsic alignment signal has been detected so far for blue star-forming galaxies. A delta plus and A plus plus here are the parameters describing the amplitudes of the projected two-point correlation function between matter field and shear, and the correlation between shear and shear separately. Both of them are consistent with 0. On the other hand, these blue star-forming galaxies are main targets of ongoing or incoming spectroscopic surveys, such as PFS and the DAISY. More precisely, the emission line galaxies are the survey targets. Emission line galaxies possesses high star formation rates and therefore exhibit a strong emission line from ionized H2 region around the massive stars. The emission line galaxy SED also shows a relatively blue continuum. For example, PFS Cosmology survey will target emission line galaxies over redshift of 0.6 to redshift of 2.4 in 1,400 square degrees scale area. The same scale area is also covered by the HSC image survey. Well, DAISY will also target 17 million emission line galaxies up to redshift of 1.6. The big incoming dataset makes us wonder, is there a way to extract the intrinsic alignment signal surrounding these emission line galaxies? So we start by looking into the galaxies in the cosmological hydrodynamical simulation. IllustrisTNG is a suite of simulation runs over 3 different volumes, from TNG 15 to TNG 300. The simulation volume increases, where the resolution decreases. So in our work, we use TNG 300, so we can have a good statistics of massive galaxies. The IllustrisTNG galaxy formation evolution model includes key physical effects, such as gas cooling and heating, star formation, stellar evolution, chemical enrichment, black hole growth, supernova, and agent feedback. It also has a cosmic magnetic field. So IllustrisTNG is found to reproduce a wide range of observational results, such as the stellar mass function, stellar mass-halo mass relation, the galaxy bimodal color distribution, and so on. We select emission galaxies by ranking the galaxies according to their star formation rate. And then we only select the galaxies with the highest star formation rate and did a cut when their conmoving number density reaches 10 to minus 4 per megaparsec cubic, which is a typical number density of emission line galaxy survey, such as PFS and DAISY. Previous study using a semi-analytic model, and the ongoing study using IllustrisTNG shows that the star formation rate around selected galaxies roughly corresponds to the oxygen to emission line strength selected galaxies. We did a selection in 4 redshifts. So This table summarizes the properties of the emission line galaxies in our sample. 90% of the emission line galaxies are centrals, and they are quite massive. For each emission line galaxy region, we run the ray tracing simulation using the stellar population synthesis code called Pegasus 0.3. Attenuation due to the diffuse interstellar medium and dust is taken into account in the code. The first panel shows the I-band projected luminosities surrounding an example emission line galaxy in observer frame in the simulation. The line of sight length for projection is 1 megaparsec, and the region size is 1 megaparsec times 1 megaparsec. Within include the sky background noise and a seeing effect in the image, assuming 0.6 arcsecond seeing, and assuming we are observing with Subaru telescope. The simulated image is shown by the middle panel. We develop an aperture shape estimator based on the simulated images. The aperture initial tensor uses all pixels with signal-to-noise ratio larger than 3, within a radius of 500 kiloparsec in moving space, centered on the emission line galaxy. Comparing to the commonly used reduced initial tensor, the newly developed aperture shape estimator includes the outer part surrounding emission line galaxies, and it gives more weight to the outer region. With the initial tensor measured, we can then calculate ellipticities and also shear. The aperture shape estimator is found to capture very well the intrinsic alignment signal surrounding emission line galaxies with a rather high signal-to-noise ratio, while the traditional reduced initial tensor gives no detection. Here, we mainly focus on the relatively large scales since the intrinsic alignment mechanism working at small scales are different. The gray squares here are the intrinsic alignment measured using the decameter particles within the halo, centered on the emission line galaxy. The aperture initial tensor newly developed by our work gives the intrinsic alignment signal comparable to the one measured from the matter distribution. Such signal doesn't depend strongly on the signal-to-noise cut used in the simulated image. It also converges with varying aperture size according to our test. The good agreement between the flux-based aperture initial tensor and the decameter halo particle-based initial tensor suggests that the light distribution follows the matter distribution, which is supported by the good correlations between the ellipticities calculated using light, which is shown in the y-axis, and the ellipticities calculated using matter distribution, which is shown in the x-axis. However, even though a scatter between those two ellipticities exists, the intrinsic alignment signal of those two initial tensor agree with each other rather well. We then fit the measured intrinsic alignment signal using nonlinear alignment model. The matter field power spectrum here is measured directly in the simulation. Only relatively large scale data points are used for the fitting. as highlighted by the blue shade. The intrinsic element of the emission line galaxies with a fixed number density show no clear redshift evolution. Such trend is likely a result of the weak redshift evolution of the stellar mass. As shown by the table here, the mean stellar mass increases no more than 0.5 dex from redshift 2 to a redshift 0.5. Our previous study in TNG 300 showed that at given stellar mass, the intrinsic element of galaxies have weak or basically no redshift evolution. To summarize, we developed an aperture shape estimator which captures intrinsic element signal surrounding emission line galaxies with a high signal-to-noise ratio. This method can be promisingly applied to future spectroscopic and image surveys over the redshifts where the cosmic deformation is violent. This is making intrinsic element measurement useful to constrain cosmology and galaxy formation. Thank you for your attention and looking forward to the discussion.